Hi guys, my name is Elise Ahmad, and this is my brother Noah.
Hello.
And we are going to be learning the auditory pathway today.
Yeah.
Yeah! So we've already done 2 videos and they've all been over time, so hopefully this one is under time, and hopefully Noah is becoming an expert in auditory pathways.
Well, I am.
So sound. You hear sound. Sound, we all know, is air compressions, right? And so these air compressions are collected by our outer ear and directed towards our middle ear. This part of your ear is called the pinna, and it's shaped sort of like a cone to collect sound, which makes sense. The sound travels through the ear canal, which is about 2 centimeters in length, and the ear canal serves to amplify sound. Okay, very important, because when the sound waves get to the end of the ear canal, they get to the eardrum, which is also called the tympanic membrane. You can think of a timpani, which is that big bowl-shaped drum that has a thin membrane over it. Looks basically just like your eardrum. So when the eardrum vibrates, it causes these 3 bones in the middle ear called ossicles to vibrate as well. So that's converting the sound waves to mechanical energy. There's 3 bones. One is called the malleus. It's also known as the hammer. One is called the incus, which is also known as the anvil. And one is called the stapes, which is also known as the stirrup. And these are all based on the shape of the bones. I'm not going to lie, I don't really see it. I only kind of see the stirrup, which is this little guy right there, and it's literally because it looks like this.
Like a stirrup.
Like a stirrup. Who knew? This also amplifies sound because the malleus is about 15 times larger than the stapes, so it's greater in surface area. So the pressure or the vibrations felt by the stapes are I don't know, of greater amplification. That's all I can think of right now. Sorry, words. So the stapes. Sorry. Text from the other brother. We're at the library. So the stapes. No, I had a heart attack.
Why didn't you text me?
The stapes vibrates at something called the oval window. It's also called the vestibular window. And this is at the entrance to the inner ear. Your inner ear is comprised of this network right here, this network of canals. You have these semicircular canals, and these have to do with your balance and the direction that you tilt. They basically tell your brain that you're tilting your head, which makes sense. When you hear a sound and you don't know where it comes from, you tilt your head to listen for it. The other part of your inner ear is your cochlear. Plural is cochlea. You've probably heard that term tossed around a little bit more. So the oval window is right here at your entrance to the cochlea. And the oval window, your cochlea is basically a series of fluid-filled sacs. So when this oval window vibrates, there's vibrations in this fluid. So now before we were at mechanical energy, now we're kind of talking about hydraulic energy. Okay. Yeah, check that out.
Awesome.
So you can't see it because I'm horrible at drawing, but this spiral is not actually flat. It rises, sort of like a cake, kind of like that. So it literally goes upwards. So this little part is called the apex of the cochlear. Cochlear. Okay, great. And so when the oval window, this is your oval window, and this is the round window. When the oval window vibrates, it causes vibrations in the fluid in the cochlear. These vibrate all the way up and to the apex and then back down, okay, back down this way to the round window. All right, so you've basically got this semicircle or this spiral of vibrating fluid. In the middle, you've got the basilar membrane. This is the part where there's a ton more detail that you can go into, but we're trying to keep this under 10 minutes. So, on this, there's a basilar membrane in the middle of these two sacs. And this basilar membrane contains all these tiny hair follicles, or hair cells, called stereocilia. Okay, and when the stereocilia are moved by the vibrations, they cause small ion channels to open. Those allow cations, your calcium and your potassium, to flow in, depolarize the nerve cells. That depolarization is then connected and sent down to the auditory nerve, okay? And that is that's what stimulates your auditory cortex. So that's how the ear turns air pressure into electrical signal that can be read by your brain. Now, two things. One, how do we tell loud sounds from soft sounds? Well, if it's a loud sound, it's going to be a greater number of hair follicles that are stimulated. Hair cells, excuse me. If it's a soft sound, it's going to be a smaller number. If it is a high-pitched sound, there's going to be a greater amount of vibration at the base. There's going to be greater numbers of hair cells stimulated at the base of the cochlear. Okay? If it's a low-pitched sound, like a drum beat, it's going to stimulate hair cells that are closer to the apex. Okay, so closer to this top portion. This is called a tonotopic arrangement. Okay. There is some debate on this theory. There's also something called the frequency theory, where people say that the frequency at which the hair cells stimulate electrical activity is how we determine this, but pretty much the tonotopic arrangement is I think one of the best ones out there. And there you have it. That's the ear. Hope you liked it. You get it, Noah?
I sure do.
Awesome.